Douglas Starnes is a polyglot ninja and technical community influencer in the Memphis area, making stuff that works on more than just the web. He specializes in the fields of data science, machine learning, and mobile application development. Douglas is the co-director of the Memphis Python User Group, Memphis.NET User Group, Memphis Xamarin User Group, and Memphis Power Platform User Group, as well as an organizer for the Scenic Cities Summit and a co-founder of TDevConf, a virtual conference presented by the .NET user groups in Tennessee. Outside of being a geek, Douglas is a trained composer and avid Lego collector. Have at it.
All right. Well, thank you very much. Thank you very much for having me this evening, and thanks for everybody for attending. Can you see my slide?
Yes.
Okay, awesome. Great. It has been, I actually don't know if I've ever presented on GoToMeeting before. I've definitely attended on GoToMeeting, but I don't think I've actually ever presented on it before. So this talk here is one that, well, they're all continuing and evolving, but this one I think may be evolving faster than some of the others. And we'll see what we'll see as we go along. So it's kind of Microsoft is investing a lot in this space of machine learning, and they it seems like they're kind of going in their second phase of this, and the first phase was dedicated a lot towards Python and R because those are the kind of the predominant languages in machine learning, and now they're revisiting everything and beginning to bring the .NET folks into the fold more. So there's a lot of stuff that's rapidly changing. I've actually got some stuff in here that I'm going to show that's actually in preview. It's not quite baked yet. In fact, one of my demos I'm not actually going to be able to do because one of the tools that I use updated today, and now my demo won't work anymore. So, but at any rate, I'll still be able to talk. I'll still be able to talk to it and show you some things. All right, let's see here. There we go. So I won't go through this too much because Stephen already read the bio. A lot of this stuff is kind of goes over the same stuff, but I call this the obligatory narcissism slide, which is basically about me. I am in the Memphis, Tennessee area, actually a little bit to the east of Memphis, a little town called Oakland, in the next county over. We are actually under about a foot of snow right now. Very unusual for us, incredibly unusual. Knock on wood, we have not lost power, but of course, Murphy's Law, I'll probably lose power. You know, it's probably the first time during the whole thing that I've lost power tonight, but at any rate. I bill myself as a professional explainer because I don't like to call myself necessarily an author because it sounds like I'm sitting around waiting for inspiration for the next great novel, but I am technically an author. I do mostly video content. I've done some written content, but Pluralsight is who I work with a lot. I've done a little bit of work with also a company called Real Python out of Canada, and also a company called Skillshare. Again, user group. I also help organize conferences, and I am a Microsoft Most Valuable Professional in Developer Technologies for Python. Now, you see Python, you may be thinking, hang on, what's this guy doing talking to a .NET user group? Well, first of all, that's just the area that I was awarded in. I am not primarily a .NET programmer, but however, again, big fan of Xamarin, have been for many years, even before it was acquired by Microsoft. And so, so I've definitely been involved in the .NET space. And but the reason why I do this talk, this ML.NET talk, or not necessarily ML.NET, but just .NET for machine learning, is because as a Python person, one of the main things, Python is, like I said earlier, Python's one of the most popular languages for machine learning, and so picking up the .NET side of it is just kind of a natural transition. I also do a talk about JavaScript and machine learning. So so I'm more of a machine learning person than I am, I would say, one specific language, and I also do a talk about Azure and machine learning. So I'm very interested in machine learning first, and then the specific implementation more or less second. But I do tend to use Python most of the time. So I want to start off first of all by going through and kind of doing just a hopefully brief overview of how we got to machine learning. What is it? Because conceptually, because you if you're coming tonight expecting to see a lot of deep code dives, that's not what it's going to be. I was explaining kind of, I don't know if some people may have heard the explanation beforehand, um, when I was talking before about before the presentation started about how machine learning and artificial intelligence fit into application development today. And I was saying that many years ago, I used to quote a tweet that I saw that said, without a connection to the cloud, your phone is nothing more than an Angry Birds player. Um, and what it was saying was that when smartphones were first released or whatever, that having a constant network connection or a fast network connection or a reliable network connection, it was a novelty. And then later on, it moved to something that was nice to have. And then, but at this point, it had actually moved to something that was a requirement, or it was assumed. It was an intrinsic part of the application. And the same thing sort of goes now as what we're seeing is the same thing with artificial intelligence and machine learning. First of all, it was like, oh yeah, that's really neat. And then it came and saying, yeah, that's useful. I mean, that'd be nice to have in my application. And now it's something where everybody expects it. You expect, things like voice assistants are expected, image analysis, all these things, they're now expected. So and that's what the talk is about how you can integrate it in your application without having to be a machine learning geek. But to get to there, understand what we're talking about. So there's this field called artificial intelligence, and it's been around for a long time, 60, maybe 70 years. You can even go back and say it's been around for over 100 years if you go back to the idea of the Turing test back in the early 20th century, back in the, like 1910s, I believe. And one thing I want to go through first off is just the goal of artificial intelligence. And the goal of artificial intelligence, first of all, what is it not? The goal of artificial intelligence is not to mimic human intelligence. And the reason I make such a big deal out of this is because we see this word intelligence and we automatically think of the brain, and we think of how does the brain, a human brain or any brain work, and the very little, if anything, that I say tonight is going to be related to neuroscience. And the main reason is because we don't understand human intelligence well enough to mimic it or recreate it with C#, Python, Lego bricks, or anything else. We just don't understand it well enough. Come on, why am I not? There we go. So let's take a look at an example of what artificial intelligence might do. So there's this thing called an expert system. This is just one example of kind of an early attempt at artificial intelligence that actually worked. I mean, these were actually used. But conceptually, you would have an expert and you would have a programmer. And the expert would start to bear their intellectual soul to the programmer. And this is the example I always use, but it's actually even more relevant today than it is in the past. But at any rate, the expert, say they're a meteorologist, an expert in the weather, and they might say if the temperature is 32 degrees or less and there's precipitation, it's snowing. Well, the programmer would, and this is kind of Python pseudocode, but actually that is valid Python. But at any rate, you can still see what it's saying if the temperature is less than or equal to 32, and there's a variable named precipitation that's equal to true, then the result would be that it is snowing, and otherwise that it would be raining. So what's happening here? What we have is we have code here that would hopefully have the same, that would have to come to the same conclusion as an expert would, or give the same response as an expert would. So, but what we're talking about here with weather generally is forecasts. And a forecast is a prediction, in this case, a prediction of the weather. So the goal of artificial intelligence is to make predictions. Okay, let's take another look at this. So if we have a user that goes to our artificial intelligence system, our expert system, and tells it that the temperature is 28 degrees and there is precipitation, then the expert system or artificial intelligence system should say it's snowing. Okay, take that a step further. What would the expert say? The expert would agree. So what we could do is we could expand this definition of artificial intelligence to say that the goal of artificial intelligence is to make predictions that mimic human response. not human intelligence, but human response. So now with that concept in mind, we can go further and look at what's machine learning. Now, machine learning is actually a subset of artificial intelligence. It's a subfield, a subdiscipline, if you want, of artificial intelligence. So the goal of machine learning is still to make predictions that mimic human response. But there's a twist. You notice that with the with the so-called expert system, that the code, everything was explicitly it was more like you were porting from English in that case to a computer language of some kind. And actually that turns out that when you're hand coding or hard coding all of the rules that will lead to making the predictions, there's a lot of problems that come with that. First of all, experts are expensive, experts are opinionated, being able to things are lost in translation, being able to be very thorough and catch all the edge cases. It's very difficult. So the goal of machine learning is still to make predictions that mimic human response, but without being explicitly programmed. Let's take a look at what that means. So if you have machine learning, and let's say what we're going to do is we're going to take a data set, a whole bunch of examples. So here we have a weather data set, and so we're saying that if the temperature is 70, humidity is 60, and it's in July, that you're in Dallas, Texas, it's going to be raining. But on the other hand, if the temperature is 25 and if you're in January in Chicago, it's probably going to be snowing. You're going to have a whole bunch of these things. And we're going to take this data set and we're going to actually partition it into two pieces. So each one of these columns up here, we call that a vector. And I'm sorry, a feature is what we call it. We call it a feature. And a feature is an interesting data point. It's something that's of relevance of the problem that we are trying to address with machine learning. And then we have a certain set of these features that are called the feature vector. And then we have another one that's called the target feature. Or sometimes you have more than one. See here, yeah. So this is also can be expressed as you can say independent variables and dependent variables, because this forecast, this target, depends upon the values of the feature vector. So what we want to be able to do is we want to be able to have a machine learning system that we say, okay, we're going to give it a temperature, humidity, date, and location. And it's going to, based on analyzing all this data, it's going to give us it's going to predict a forecast, hopefully accurately. So what we're going to do is we're going to pump this into some kind of a machine learning algorithm. Now, in this case, the algorithm is called classification. We'll see, another example of classification later on in code. However, classification is one of the, kind of killer machine learning tasks. And what happens is you have a set of labels, a set of well-defined labels that you are trying to, and you're trying to take each feature vector and you're trying to associate it with one of those labels. So in this case, we have rain, snow, we could have clouds or sun. And what we're going to want to do is train something called a model. And we're going to, when we have that model, we will then give it feature vectors that it's never seen. And hopefully it will, again, predict a correct forecast. Now, what's a model? And I go into this and I explain this for a particular reason. So a model, the pedantic or kind of academic definition might be that it's a representation of the knowledge, and again, knowledge is in quotes because again, we're not talking about human knowledge, we're talking about a representation of knowledge that's derived from analyzing data, and that data is that data set that we split into the feature vectors and the target vector, the feature vectors and the target feature. Take a little bit deeper look at how this works. So let's say that we have this data set here, and that we have, whoops, I think I have, well, okay, anyway, it's a little interesting. Okay, but anyway, that didn't quite come out right. But anyway, so I've got these two columns over here as the features, and this column over here is the target. Now, if you look at the association between the features and the targets, you'll see very obviously that this is representing addition. Now, the way that we might see this playing out is that when we start training, we might say we're going to take those first features, 3 and 4, We're going to toss them into the model as it's been trained so far, and we might get out a prediction of 200. This is our first attempt at it. And of course, that's going to be wildly off. Now, notice that this model has a shape. And I like to say that the model kind of fits the shape of the data, because what will happen is we will, that animation is going to repeat every time. Okay. That model, what will happen is as we begin to train the data further, as we begin to train the model further, and it sees more diverse types of data or more diverse examples, that the shape of that model is going to be refined. So 8 and 2 is 10. Maybe it'll say it's 101, and that's not as much off as our first prediction, but it's still pretty bad. So if we keep going, then maybe we go to negative 1 and 3. Notice that the corners are beginning to are getting much sharper, and then when we finally get to the last one here, in which we get the correct prediction, or a prediction that's very close to correct, and we have a shape that's going to fit closer to the data. Now, in real life, you would have millions or even billions of examples, and you would go through them multiple times. I mean, these things can take days or weeks to train. But the idea is that as the model sees more and more different types of, or more diverse examples of the data that you're going to use to train it with, that the model will become more and more refined and hopefully eventually accurate. Now, remember that I kept on emphasizing that human response is the goal and not human intelligence. That's because the model, while it's a representation of the knowledge derived from analyzing the training data, in reality, it's just a big glob of numbers. And those numbers are adjusted over time in order to make more accurate predictions. So instead of trying to figure out how the chemical processes of the brain work and represent those in code, we're actually just trying to get to the correct response. In other words, if we had that model which was again a square shape, and we give it new data, give it a new feature vector 6 and 3, obviously we expect the result to be 9. Okay, we think of this in one way, but this actually might be somehow, the model might take the scenic route. I mean, it wouldn't take this exact process, but it would take the scenic route, perhaps. And so you've heard that the end justifies the means. Well, that's actually pretty much the case in machine learning and artificial intelligence in general, because you saw how the expert system, how we work the expert system, it definitely did not try to mimic the processes of the human brain either. A little bit more deep learning. I'm not really going to talk about deep learning tonight. Deep learning is a subset of machine learning. This basically talks about machine learning with neural networks. So I guess you could say that that's trying to mimic human response or make predictions that mimic human response without being explicitly programmed using neural networks, I guess you could say. And some people will even go further and say that reinforcement learning is a subset of deep learning. But that's beyond the scope of this discussion tonight. Then there is some people sometimes say, well, where does data science come in? And data science, I like to say that it's related but separate. A lot of techniques that you'll use, especially in the Python world, for data science are going to be used still in machine learning. And then actually in ML.NET, some of the functionality that you would find in a Pandas or NumPy has actually been built into ML.NET. So definitely data science is something that you can't get away from, but it is a separate discipline. Data science is more looking at things in the past and saying what happened in the past, and machine learning or artificial intelligence is more saying, hey, what's going to happen in the future by analyzing the past, I guess. So what is machine learning capable of? Well, we already talked about classification. Another one, regression. This is more dealing with continuous values as opposed to a finite set of discrete labels. Clustering. This is basically looking at data that is not already labeled and saying, hey, what's interesting about this data? Find me commonalities within this data and group them by their commonalities. Recommendation. So Amazon.com. Making sure I'm staying on time here. So Amazon.com, hey, you bought this product, and these 100 people bought this product, and these 100 people also seem to like, this product. You might like it as well. Anomaly detection. I always talk about the, old Sesame Street skit that, which one of these things is not like the other. So basically finding what does not belong in a particular situation, such as I always talk about machines that are running, and you're monitoring specific metrics on the machines, and if something, if something goes out of line, out of the norm, then maybe that machine needs to be looked at for maintenance or something. All right. So let's talk about how does this come into ML.NET. So I'm going to go through a quick kind of walkthrough of the workflow of ML.NET, and then we'll see it in code. Now, ML.NET it's a library that I think it's been released for about a year now. It's actually been the stable release. I think build last year. For some reason, I want to say build last year was when it was the stable release of it came out. However, it is a library for machine learning that is written with .NET in mind. And actually, I don't think I have it in this deck, but I can probably go online and find it. There's a really, really interesting, and I really like the image. It takes, because ML.NET is not the first attempt at machine learning in .NET. There's the whole, what is it, Sci-Sharp project or something? Sci-Sharp project, I forget. But anyway, it's a group of technologies that are actually more or less ports of Python projects, so such as NumPy.NET or Pandas.NET, TensorFlow.NET. You may have heard of TensorFlow as being, as the machine learning library from Google, the deep learning library from Google. The thing is, when you look at those, when you compare the Python versions of those to the .NET versions of those, you can see that the .NET versions are actually more or less just a port of the Python APIs in many cases. And that does, and while it works, it's not code that's bad or anything. It's not necessarily wrong. What you're basically taking is of course, these libraries are written with Python in mind. They were written with Python first. And so they follow things like Python idioms and best practices for Python. And when you just take those APIs and port them over to C#, you're actually enforcing or trying to superimpose those idioms into a language where they're unfamiliar. So that doesn't always work. So ML.NET is written with .NET developers in mind. And one thing is that it's very object oriented. So for example, the features and targets are represented in classes. So this first example that I've got here is predicting housing prices. So it's going to be regression, and you would have a class here for your house data. So you might be relating size and price, and then also you're going to have a class for your prediction for what's going to be predicted, which is only the price. Now this column name attribute, that's something that comes out of ML.NET. I put it in, I included in there because it's included with the example. It's not really used in the example, but you're going to see also that ML.NET goes to great lengths to allow you to make your data, to make it to where you can describe your data to ML.NET as extensively as possible. And in doing this is one way. And also other things are like making sure the order of columns is maintained and other things. So they try to idiot proof it where, well, I don't want to say idiot proof it, but they try to make it as safe as possible. Whereas Python, you would just give it a CSV and a raw CSV and say run with it. And that's very much how Python operates. Python is, it's a very, I don't want to say free for all, but it's a very loosely regulated language. What is it? There are actually something that people are very in Python that they're very surprised to hear is Python has no access modifiers. Everything technically in Python is public. But like I said, it's a very more loosely organized language than a strictly object-oriented language like C# or Java. So you're going to have classes that are going to represent your feature vectors and your targets. And then everything's going to start off with this thing called an ML context or machine learning context. So you'll create one of those, and then you're going to somehow get some data in. Now, like I said, this could come in many different ways. So in this case, what I've got is I've just simply got an array of these house data objects. You could also pull in from a CSV, being a Microsoft product. There are ways to come in from different Microsoft sources such as Excel. Now, like I said before, ML.NET tries to make it to where you describe your data as extensively as possible. Down here, again, the data source that I'm using is this array of house data, but passing into the load from enumerable file or load from CSV or whatever. But however, it's a generically typed method. So you're going to tell it, hey, this is going to be the type that I'm going to be using, as opposed to just an array of numbers that could mean that have no meaning attached to them. You're going to create something called a pipeline, and a pipeline is going to exist of various, generally a lot of transforms on the data. Now, this one here, all it's doing is just combining all of the features into a single value to make things easier to handle for ML.NET. But we'll see an example later having to do with text, where we'll do something called featureizing text, and then putting caching points in there. These transforms are something which generally in Python would actually be, like I was talking before, might be handled by a data science library like Pandas or NumPy. But however, that functionality has been built into ML.NET. So after you've got your pipeline set up, then what you'll do is you'll select an algorithm. Like I said, this is a regression problem here. The algorithms are called trainers in ML.NET. We're going to tell it what do we want to predict, what column are we wanting to predict, price in this case, and then maximum number of iterations. Remember I said that as the algorithm sees more diverse examples of data, it's going to be able to refine the model and fit the model to the data better, so that it will make more accurate predictions in the future. And one of the ways that it does this is by going over the data set more than once. So remember that first prediction on that first iteration, that was wildly off. We want to be able to get a second chance and a third chance and a fourth chance at it. In this case, 100 chances. And what's the ideal number to use here? Unfortunately, the classic answer of it depends applies, because it is something that depends on your data, the problem that you're trying to solve, and all kinds of things. But at any rate, this is just a generic look at the workflow. So we've got our pipeline, and now we want to actually train the model, where all the heavy lifting goes. And like I said before, this is sometimes referred to as fitting the model to the data. And of course, I had that training data that I brought in, passed that into fit, to call that on the pipeline, and that will return us an instance of a model. Then what we'll do is we'll create some new data. In this case, we only have to give it a size because we're going to predict the price. Create something called a prediction engine. Notice that the prediction engine is also a generic method, or the method that creates it is generic. And so basically what it's looking at is it's going to say, okay, I want to have a prediction engine that's going to take a type called house data, and it's going to return a type called prediction. So it's not just going to return a single value, it's going to return a strongly typed object. Again, allowing you to describe your data to ML.NET as extensively as possible. And then finally, call predict on the predict engine, passing it the test value, and that will get you your prediction, and you'll be able to inspect the prediction object and see and get the results out of it. Also, what you can do many times, especially while training the model, you'll want to test it on a testing data set, so you can have an entire set of testing data. You can load that in. It is actually possible for ML.NET to try to infer the types of the data that you're using, but generally want to use the generic methods. And then what you can do is you can get a whole bunch of predictions at once by transforming the test set using the model into a series of predictions. And then what you could do is you could there are a number of evaluation metrics also for each type of problem, such as regression or classification or what have you. And in this case, you take the predictions, tell them that you're wanting to look at the price and make some kind of and get some kind of a score for the accuracy or whatever. And then
Okay,
there's
Doug,
also.
we've got a question in the
Oh, okay.
comment.
I'm sorry. I'm
Oh,
not
no
looking.
worries.
I'm not looking at the chat. Okay, so what options for scaling of the training? Can you use GPUs? Yes, you can. GPU support absolutely is. I'm not going to go over it tonight, but yes, you can get GPUs. And actually, that's thank you for the question, because that gives me an excuse to talk about why that question is being asked. And actually here, after a while in a demo, we'll actually be able to see how taxing even the smallest problem is on an 8-core CPU. But so the idea is, as I've talked about before, this is all very mathematical. It's all, again, it really has nothing to do with neuroscience. It's more math than it is neuroscience. So we're doing lots of mathematical operations over and over and over and over again. And that's very taxing on a CPU. A CPU is not necessarily designed for, it's designed to be more of a generalist. Now, however, we have these things called GPUs, also called graphics processing units, and you might normally think of them as being associated with video games because video games are very graphics intensive, and actually, when you're rotating models or putting together polygons or whatever, that's all just a lot of math. So GPUs are kind of specific processors that are specific towards math in a way. They're tuned for mathematical operations. Well, it turns out that the GPUs and excuse the noise downstairs. It's feeding time at the zoo. Animals are not being slaughtered. But at any rate, the beagle really gets upset when she thinks she's not going to get fed. But the GPU really doesn't know what it's looking at. It doesn't know, am I looking at a model of a 3D of a hero in a video game, or am I looking at a model in a machine learning project? It doesn't know. It doesn't care. It just knows math. So you can actually offload at least some of the work while training and such in machine learning onto a GPU, and it will be much, much faster. I don't have an example of how much faster it will be tonight, because I'm running mostly small problems. Because, like I said before, the real world problems can take days or even more to train. So you wouldn't really see a lot. You wouldn't really see a lot of difference with the small problems that I want to be able to train tonight. However, like I said, we will see an example of how taxing it can be on the CPU later on. But yes, definitely GPUs are supported. What about across multiple computers? That one with ML.NET directly, I'm not sure. I know that there is, however, ML.NET, however, with Azure Machine Learning, I know that with Azure Machine Learning, you can set up compute clusters, and you can very often, and what I would very often sometimes in that situation recommend is that you put your problem out on Azure Machine Learning, and then export the model, and then bring it down and import it into ML.NET, and we'll see, kind of a simple example of doing that, because I actually think that's probably right now kind of the killer application for ML.NET is being able to import models from other sources and bring pre-trained models into a .NET application. Okay, and if I miss questions, I'll try. I'm going to move. Let me move the chat over here. You're going to see it just a second. Okay, I'm going to move it over here to this monitor so that I can see it easier. All right. So this was an example of regression. Again, regression, if you're not familiar with it, if you may have heard of linear regression, you have a set of data points, and what you're trying to do is you're trying to find a model that fits them. You might do something like this. You might have a line that tries to minimize the error, the distance between each data point and the line. So then maybe, what was I, hold it. All right. At any rate, so then what you might do is later on you might say, hey, I've got a point here. This is the value for which I want to make a prediction. You follow up to the line and you say that's the value where they meet is the prediction. Okay. So let's take a look at this. Yeah, time to look at code. All right. So let's see here. And another thing that this is actually the first time that I am orienting this talk around Visual Studio. I used to actually orient around Visual Studio Code, and so hopefully that will work out. Now, really, what I've got here in this application is really just the same code that you saw on the slides, just organized better. So, and this is actually one, in fact, I think all of the examples that I use come from Microsoft because there's only a limited number of these examples that are really small, that you can, small and relevant, that you can train by clicking a button, and it only takes a few seconds. But at any rate, so again here, using the Microsoft ML library, there's actually a NuGet package over here, my NuGet package, Microsoft.ml. Again, I've got my classes here for my feature vector, my targets, and then my ML context. Take you create your training data, bring it in. Here's the pipeline. Again, just the exact same code you saw on the slides, fitting the model to the data, creating test data, creating a prediction engine, and then make the prediction from it, print out the results, see what happens here. If you look up here, what this is saying is that a 1,100 square foot house would be $120,000, and that a 1,900 square foot house would be $230,000. Basically, what it's saying. So here it's saying that a 2,500 square foot house would be about 277,000.15. Remember that number, because I'm going to run this again. And now it's coming up 276.48. And I'll run it one more time. Notice it comes up 273. Hang on, let me kill that to get rid of some notifications. There we go. Notice that it's coming up different every time. This is the exact same data every single time. Actually, it's training a new model every time. It's just so fast. It's just such a small problem that you can't tell. And this is something else that I want people to know, is that the process of making these predictions, we're not necessarily trying to make predictions that are 100% correct. We're trying to make predictions that are as close to correct as possible. Notice this is always going to revolve around kind of the mid 270,000 range, no matter how many times you run this. And again, these are predictions, also called approximations. So you can think of it that way. But that's kind of the second big takeaway, is that you're never really going to have anything that's actually 100% accurate. But if you think of the whole meme about the uptime with more nines, please, you want 99.9999999%. You want to get as close to perfect as possible, because nothing's ever going to be perfect. So that's just kind of ML.NET in a nutshell. Now I've got one other example I'm going to go through very quickly, and I'm not laboring over the code really for a reason. I'll get to that reason later on, but I do have one more example here that I want to show you, and I'm going to show it for a reason. Where is it? Okay, this one. Now this one's actually an example of classification, so a little bit more involved. That's that. Okay, I hope this is correct. Yeah, that's right. Hold it this one. Oh, this is right. Okay, that's right. I'm gonna get rid of the one. There we go. Okay, so this one first of all, let's take a look at what we're looking at. So this one is a classification model. There's a whole bunch of GitHub issues that have been collected into a PSV, tab separated file, which is like a comma separated file, except it's limited with tabs. And the two things here to keep in mind are this area, which in this case would be system XML, and a description, which is talking about XPath document queries failing. So what we're going to be doing here is we're going to be creating a model that will take the description of an issue and categorize it into a correct area. I think basically this would be dealing with the namespace or assembly to which the issue is related. Okay, so if we look over here in this issue GitHub issue data, you're going to see that we have a class for our issue, which is going to be the data that which could be the feature vector, and then the prediction, which is we just want to predict the area that it goes into. Again, we're going to have a context. We're going to have a prediction engine. You're going to have the training data. So right here, this time instead of loading from an enumerable, we're going to load from a text file that has a path. This input here has header. We'll make it skip the first row of the data. Then other things that we've seen before. Here's the pipeline. Like I said, it was going to be more complex this time, because what we're doing is we're featurizing. One of the things we're doing is featurizing the text. Featurization is, like I said, everything's mathematical in machine learning. We want to work with numbers, and what featurizing does, it takes text, takes a corpus, a body of text, and turns it into a numerical vector. And so it makes it much easier for a machine learning algorithm to work with. Here, this little optimization thing in here, being able to establish checkpoints and cache the progress. Let's see here. Here's where we're fitting that. Here's where we're actually training the model. Then down here, here's creating the prediction engine, creating test data, and then making a prediction. And then down here, going through and with the evaluation metrics again. There's also, in this case, there's also persisting the model. So one of the things is that you don't want to train every time you have a new prediction to make. You don't want to retrain the model every single time, like in the previous example. That one worked because it was short. You want to persist that model and then just load the model in the future and then make predictions off of that loaded model. And that is happening. Where is it happening? It's in this one. Yeah, right here. So where we're loading the model up, and then after that, it's just the same. You create a prediction engine and make a prediction. Okay, so this one I'm going to go ahead and run it because I want to get that trained model, and then we'll see how all that's really required to use a pre-trained model, which is not really that much. It's just that code right there. Now, one thing I also promised you is, let's see here. Where is? Oh, I lost it now. Crud. I lost the window. Oh, okay. Oh, I lost it. That. Well, I lost the window that shows the CPU. Well, actually, here I'll do it the old-fashioned way. Oh, boy, it is eating up the time. Okay, what you can see here is that I actually have, I don't know why that's open. That should be gone. That'll help a little bit. But okay, I'm going to start. I'm sorry about that. I'm going to start that again. I lost the. Here we go. The diagnostic tools. That's what I wanted. Okay, now let me run this again. I'm going to start all over again. You'll notice it while it's training the model. Come on, view. Where do they hide those over here? Diagnostic tools. There we. Is that what I want? Oh, good grief. Well, why does it hide them when I start the build? Normally, okay, at any rate, we'll go back to the task manager. You'll see that Visual Studio is pulling a large amount of my CPU here. And that's what I was talking about before with GPUs. That would not be as, even though I do have a GPU in this machine, I just don't have it set to use it. That would be, but normally there's a graph over here, and at this resolution, it goes away. Okay, whatever. But you'll notice while this is training the model, this does take about 30 seconds to train, and because it's crunching numbers. So this should be done here in just a second, I think. I wish I could find that. I wish I could find that window. Diagnostics. At any rate, I think it's done now. Okay, so I'm not necessarily worried about these numbers right now. The big thing that I want to talk about is that this model was saved. Okay, and it was saved over here. Well, actually here now I don't know why it comes back when the application stopped running, but you'll see here at this processor that the processor was often spiking close to or right at 100%. And like I said before, this is an 8-core processor. This processor is only about a year old, so it's a fairly recent processor. And still, even this very small problem was taxing it quite a bit in some places. So, but the big point that I want to make is that I do have this model here, and the file, if we look inside of it, it's not really anything. It's not anything to write home about. It's just right here, I believe yeah, these are the well, you keep on digging down deeper and deeper, but still, it's not something we're meant to look at. It's something we're meant to just use. So I do want to have that in a folder over here because I want to drag that into the project, new one. So, but what I said is, like I said before, this is kind of one of the what I think is one of the kind of the killer features of ML.NET is the ability to bring in a model that's trained not necessarily from ML.NET. It could be trained also. It could be trained, for example, in TensorFlow, and brought in. There's an open file. There's an open format, an open standard for expressing and describing machine learning models called ONNX, ONNX. And that also can be used to bring in, to export models from ML.NET or bring models into ML.NET. But what I want to do very quickly, and this is an absolutely, I should probably pay somebody to actually make me a good web application. But all this is the most basic ASP.NET Core application that you can make, ASP.NET Core Razor Pages. And I am not a web developer at all. I try not to. Okay, so what you'll see here is I have a folder called pre-trained. I'm going to open that up. Going to come on. Come on. Where is it? There we go. And going to take the model out of here, copy it. I'm going to paste it into this pre-trained folder. And then going back to Visual Studio, there we go. Going back to Visual Studio, if I go over here to this page, where did I put it? I put it in the index page, I think. You'll see that down here, I've got a form that's bound to that GitHub issue again. It's going to bring in the title and description. And then when it's posted, it's simply going to take that GitHub issue. It's going to load that model that I just posted in, that I just pasted into the pre-trained folder. Then it'll create the prediction engine, use it to make a prediction on the issue. So if I run this, and then if I go back over here and see here, I need to get classification. I need to get my data here. I need my training. And it's fine. Okay, so what I'm going to do is I'm going to get this title and paths that are failing, copy it in here, and then take this one. Okay, hang on. I should always practice these at the resolution I'm going to present at. Okay, C, OB. As you can see here, the area that's predicting is going to be system.xml, and then what I'll do is I kill Visual Studio again. Going to put a breakpoint here so we can examine this prediction. Back over here. Did it hit? There we go. And then if I look at the prediction down here, you can see at the area that comes back with this area is system XML. So in that way, like I said, this is all that you have to do to actually use that model. You don't train it every single time. You train the model once, and then use it later on, and then just make incremental updates to it. Now, so like I said, that's that's another one of the takeaways that I want you to have from this, is that you don't always have to train a model, and in fact, many times you won't need to train a model, or train a model with code. And there are other ways to train a model. So there are actually two methods that you can use. One of them is built into Visual Studio. So let's see here. If I close this solution, and create a new project, and just go to console app, call it Blood Model Builder Demo. And this is so simple. And it's so simple to do this. I can actually build it from scratch. I can actually do it from scratch. There's a There's an experimental support option. I forget where it is. Well, the first time you try to do this. So basically, what I'm going to do is I'm going to go over here and say add machine learning to a project. The first time that you do this, it'll ask you to enable some experimental support. So this part here is actually not baked yet. But this is the model builder inside of Visual Studio. And this is something called automated machine learning. And this is one of the hot topics right now in machine learning. This, along with operational machine learning, or so-called MLOps. And which is actually something I'm working on to talk about now, is operational machine learning. But at any rate, in this case, let's say that you have domain-specific data. And there are really only, in some cases, a very limited number of actual tasks such as classification or regression or recommendation, anomaly detection, whatever, that you would want to perform. And those problems have been solved over and over and over and over and over. What differentiates one project from another is the data or one model from another is the data that they're being trained on, not the method used to train them. So let's say that you can't find that there's not a pre-trained model out there, but all you need is something like simple text classification. Well, what I can do is I can use the model builder for this. And all I do in this case is I tell it, okay, I want to have a text classification. I've got a text classification problem. Tell it what data I want to use. I'm going to get it from a file. I get it from a file, or of course, since it's a Microsoft product, you can get it from SQL Server. So if I go in here, I've got this file here, which we could probably also look at. Well, actually, no. We can look at it here. This is sentiment analysis, actually, which is a form of text classification. And what we have is we have these labels over here, where 0 is meaning it's negative sentiment and 1 meaning it's positive sentiment. And then we've got a whole bunch of other columns in here as well. These came from Wikipedia. But at any rate, all I'm going to do is I'm going to tell it what column do I want to use. What is the column that I want to predict? In other words, what's my target? And in this case, that's going to be the label, whether it's positive or negative. Then also I can have my feature vector. And in this case, the only one I want to have is this is the comment itself. So I'm going to uncheck all of these, and I'll tell it I want to train. And it's going to ask me how long do you want to train for. Now, I'm going to tell it 120 seconds just so we don't wait on this thing for 5 minutes. It's going to tell me that 120 seconds is not long enough that for I've got a 16 megabyte data set, so I should probably train it for around 12 to 15 minutes. But at any rate, I'm going to go ahead and continue. And what this is going to do is it's going to start trying a whole bunch of different models, and we'll see the results down here. While that's working, I'm actually going to show you the other way to do this, because everything that I've talked about tonight so far up to the model builder is cross-platform. It's all .NET Core, so it'll not only work on Windows, but it'll also work on Mac OS and Linux. And of course, on Mac OS and Linux, it'll work inside of Visual Studio Code. Well, on Mac OS and Linux, it'll work inside of Visual Studio Code, and on Mac OS, it'll work on Visual Studio for Mac. But there is a tool, a command line tool that you can install called MLNet. And it's just a .NET .NET tool install. And I've got over here in that same folder a command line command. And so you again give it the type of problem that you want, path to the data set, what are you trying to predict, and again an amount of time to how long to train it for. Copy this. Let's see here, desktop plug MLNet. And this one will be off to the races. So this is the way that you can do. So this is the way that you can do this cross-platform. They're basically doing the exact same thing. They're two sides of the same coin. And again here, it was looking for. You can also have this one set up to use a GPU. Now we're coming towards the final seconds of this one, and then after that, it's going to ask me to take one of the rows from the training data set to evaluate the model. Come on. So which one did it select? It only had time to train 2, so it looks like it selected this one here. Here we go. All right. And then, so this one here, well, that should probably be negative sentiment. Interesting. That came out I guess it was because, oh, okay, probably because of all this other stuff. All the, it was, let's just try, let's try this again. Try this again. Let's get rid of that and predict. There we go. Yes, that would, yeah. That's, okay, that's more what I was expecting. Okay. Any rate, that's not the point that I want to make here with this one is what happens to, how do you get the model and everything out of this? Well, they not only give you a model, they'll give you some projects. They'll give you one. They'll give you one is a project with the model. So here's that zip file with the model inside of it. Then some code on how that you use to that you would actually use the model. And if you look through here, you're going to see that it's loading that trained model, creating a prediction engine, and using that prediction engine to make a prediction based on some kind of input. That model input is again a class that represents the structure of our data set and the and our feature vector, and then the output is again what we are our feature vector. Up here gives you a little bit of a gives you a small console application that again allows you to use the model in order. Is that right? Yeah, that lets you use the model. And since again this is a text classification problem, it goes through with all your featurization and everything that we saw before. Also, if we go back over to this one here, we'll see that it has also created it has also created a project for us. We look at it, it's going to do a lot of the same thing. Come on. You see it's going to do a lot of the same thing. You've got a model here, and then you've got a and you got so you've got a model here, and then you got another project of how you can actually use that model. Okay. So that is a large part of the stuff, with the exception of the model builder is in preview, or it's using preview features. So that's not quite yet baked, but that's a large part of the stuff that you can use today. Now there is something else also that this is the part that's not going to work, but I will at least show you what's going on here. So the .NET Interactive. And actually, there's a tool. Let me get my Anaconda up here, so I can at least demonstrate kind of how the tool works when. So this is in preview right now. This .NET Interactive is in preview. In fact, it only works with the Insider build of Visual Studio Code, which you can have installed side by side with the release, with the stable version. And I'm going to open up. So this is based off of something called Jupyter Notebook. Now, Jupyter Notebook is something that started off in the Python world. And like I said, this crashed today, so I don't have a really great example of how to use this. But let's say that you were going to, let's do something low-hanging fruit. And this is going to be in Python. Creating the squares of the first 10 integers, okay? So for x in range 10. Okay, and then you go through later on for x in square predict. Okay, so pretty obviously what this is doing. Now notice what's going on here. So what I've got is I've got a web browser interface. I've got these things called cells, and I'm putting code in the cells and I'm executing each cell. If you've probably heard of a REPL before, read, evaluate, print, loop. This is basically like a REPL on steroids. Because what I can do now is I could do something, say, maybe I want to cube these instead. And all I have to do is modify that, go back, modify that one cell, and then keep going forward to see the results without. I don't have to rewrite everything again. I don't have to go through and execute a whole file again. I can just execute only the code. I can just modify and execute only the code that I need. Now this is good because what happens is in the world of machine learning, what you're doing is you're running experiments, and the process for running experiments is often you'll set up an experiment, you'll set parameters, what are called hyperparameters in machine learning. basically that's the configuration of the metadata. Then you'll run your data through your experiment. You'll get your results, and you'll look at it, and you'll analyze that and say, okay, I'm going to go back and I'm going to tweak these hyperparameters. So I'm going to just tweak these. I'm going to tweak these hyperparameters, and then I'm going to run the data, run the experiment again, and such. And you're going to keep on going through that iterative. You're going to go through that iterative process. So this is not just machine learning. This is just scientists in general. And so this tool is actually set up so that you can do that. Because what happens is one of the things, if I close this and if I shut it down and open it back up, I'm right back where I left off. If I go on to GitHub and I look up Cooper, actually, hang on. Actually, if I look up fast AI, there, that's what I want. Look at something like this. If I upload one of these, IPYNB is, because these are stored basically in a, if I look at the raw, it's JSON. These are text files. They're JSON files. And what'll happen is you can have not only the code, you can also have markdown. So here's like a pandas data frame. You can have images. And the cool thing about this image is this is not a linked image. What they do is they base64 encode the images and put the base64 encoded text inside of the notebook. So you can have markdown, so you can have rich text. But what somebody could do is they can download this notebook on their own machine and start off where the author left off. So reproducible research. The .NET Interactive allows you to do that exact same thing. Oh, and look, guess what? It looks like does that mean the build is failing? That may, yep, the build is failing. That's probably why I had a problem with it today. Okay, I should always check that. But at any rate, so for example, but it lets you have that exact same workflow using .NET. So I'll just take a look here at one of the notebooks samples. And actually, here's something that's similar to that housing project that we did before. The other thing you can do is you can have visualizations in line. Lots of different possibilities. Like I said, this is kind of not very exciting right now because I'm not going to be able to run it. But but hopefully you can kind of infer the potential that's going to come out of this when it is finally baked. Let's see here. What does it do with larger data sets like I guess you're talking like petabyte scale data sets? I would assume I've never actually experimented with this using something that large. I assume you're talking about ML.NET. I would assume it would depend upon the machine that you're running it upon. So I don't know if that's necessarily a limitation of ML.NET, but instead it would be a limitation of the hardware that you're running it on. We can look into that further if you like, but that would be my assumption. So that was going to kind of be something really cool because I wanted to go through and show how you could train a model and show how you could go through that same process that we went through in Visual Studio Code of training a model, but do it more interactively, which is the way that I would actually recommend doing it, and also see a really cool tool. One last thing that I want to show you, because it is, it's 7:17 for y'all, 6:17 for me, is a tool that just a few months ago came out. Called Lobe. And I'm gonna have to switch my camera off for this because Lobe wants to use my camera. So what Lobe allows you to do is and this is also in preview. This hasn't quite been baked. This may never be baked. I don't know, but I believe this is still in preview. This allows you to very easily, and I'm probably got to turn my lights up to do this. So hopefully my office is not too messy. But at any rate, this lets you easily train computer vision models. So I'm going to do is, and this also I believe this also works cross-platform. But at any rate, I'm going to create a project, and it's going to ask me a way to bring in a whole bunch of images. Now, there's several ways you can do this. You can import images from your computer. You can. What I'm going to do is I'm going to bring them in using my webcam. And there we go. What I've got here is I've got a number of IoT devices. So I've got a Raspberry Pi, I've got a Circuit Playground Express, and I've got a Pi badge. What I'm going to do is I'm going to take each one of these. I'm going to start to, well, first of all, I'm going to give this a label. Also, I'll call this Raspberry Pi. And I'm going to start to take pictures of this at different angles. And again, one of the things with machine learning is that really helps you train a model well is diversity of data. So I don't want to just take a whole bunch of pictures of it like this, but I want to do things like turn it around, different angles, maybe get it from the sides. You need at least 5 images for each label. Okay, so there's 10 for that one. And then I'll take the Circuit Playground Express, which is a completely different shape, rotate it around. Okay. Oh, okay. Okay, hang on. Shoot. Okay. I messed that up. I forgot to, okay. I forgot to create a new label. Okay, let's do this one more time. Okay. And then let's create a new one. And we'll call this the playground. And we'll take pictures of this one. Okay. And then, come on, do one more, call this the Pi badge. Okay. And you'll notice, well, over here, it's, we're supposed to be training these. There we go. Here in just a second. Whoa. I must not have taken very good pictures with the Raspberry Pi. But at any rate, so it's trained a model for me in the background, and now I can sort of test this model out here. So it did pretty good with the Pi badge. So you'll see down here, it's giving me what the and this progress meter is kind of a it's a representative of the confidence score. So if I turn it around, actually, it thinks it actually thinks it's a Circuit Playground Express if I turn it around, but getting it from the front, it's relatively sure it's a Pi badge. And if I bring the Raspberry Pi up, I actually think it's a Pi badge. I took those pictures really, really quick. Yes, 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 it could absolutely. But whoops, that's not the one I wanted to. Yeah, no, Sam, you're right. So because actually this one it gets because of the shape. And then I've also got this one here, which is an AZ3166 chip. This is for use for IoT, for Azure IoT prototyping. And notice this one, it can't decide whether it's a Raspberry Pi or a Pi badge. And that's something else about classification, is it's going to assign one of these 3 labels no matter what. So even though this doesn't fit into any of those, I guess what it's looking at is okay, hey, it's got a display, and it's rectangular. That's what it's looking at. So it can't decide between the Pi badge and the Raspberry Pi. But at any rate, here's the cool thing about this. You can export a model from this, and notice all these different types of models. So I could export TensorFlow, which I could bring into a Python app, TensorFlow JS, and here's that Onyx again, and Onyx, which is Open Neural Network Exchange. So I could actually bring and Onyx is supported by ML.NET. So by loading it, so I could export this, use the Onyx model loader inside of ml.net, and bring this model right in and use it with the prediction engine and all the other things that we saw inside of the API. So that is what I've got as far as demos. Let's go back to the slides real quick because I've almost worn out my welcome here. Let's see here, not stuff I wanted to do. Let's see here. So let's see here. Here is basically the kind of the punchline, if you will. Actually, there is, well, no, I'll skip that. I'll skip that demo because unless y'all just really want to see it, it's not really anything exciting. But let's say you've got a machine learning problem, and this is your machine learning problem workspace. And actually, Sam, what you were talking about, yes, could it? It could, but the thing is, the background was staying relatively the same, and I was trying to hold the IoT device. I was trying to hold it kind of up in front of my face so it wasn't catching like facial expressions or anything like that. But no, you're absolutely right. It could. So let's say that this is your machine learning workspace. Well, many times if you're in, especially if you're in .NET, but really even if you're Python or Java or whatever, if you're using Azure and you want to bring machine learning into your application, ML.NET is not really the first thing you should look at. It's actually the Azure Cognitive Services. If you're not familiar with the Azure Cognitive Services, these are RESTful APIs that live in Azure, that are hosted in Azure, and they expose massive machine learning models that Microsoft has spent a long time and many resources training. And so what happens is, so for example, for sentiment analysis, there's one for sentiment analysis like we saw with the automated machine learning model. And what you would do is you would there are SDKs, or you can bang away at bare REST endpoints. You would ship some text up to that endpoint. Microsoft will do some machine learning magic on it, charge you a little bit of money, like fractions of a penny in some cases, and ship the results back to you in JSON. So you can integrate that into any application. So like I said, there's SDKs for .NET, Python, Java, JavaScript, and other languages. Or if you're using something like, say, Dart, a Flutter application, you could just bang away at the endpoint itself. The problem with the cognitive services is that these are all pre-trained models, and they're generalized models. So if you had say some domain-specific data, suppose you're going to do sentiment analysis or document classification on something that uses jargon specific to a particular industry, then what you might want to do is you might want to go out and look for a model that a machine learning model that's been trained on your industry-specific jargon. Now this is called I call this transfer learning, or it actually is called transfer learning. But basically, it's the process of bringing in that pre-trained model and then using it some other way. So what you're doing is you're transferring the knowledge from that pre-trained model into your application, and then sometimes you might even go through and build on top of it. Now, if you can't find a model trained on the data that you're using, then you might need to train a custom model, but you don't need to write code to train that custom model because you can use the model builder or the ML.NET tool. This is the automated machine learning. And then after that, because most of the time, you're going to want to do something like classification, like regression, like anomaly detection, problems that have been solved many, many times before. And we know how to train models for using those specific techniques. But again, what differentiates one model from the other most of the time is going to be the data on which the model was trained, not the process used to train the model. And then after that, if you've exhausted all of those other options, then writing custom code is something that you would want to look at. So we are right up against, like I said, 7:30 for me. I definitely don't want to keep you longer since you're in a later time zone. But that's all that I've got. If you would like to connect with me online, LinkedIn is my preferred social network right now. Also, I do stream on Twitch. I haven't streamed for a while, but on March 1st, so a week from Monday, I'm going to start again. And every Monday, I'm going to be talking about machine learning. I'm going to talk about machine learning every Monday. It'll probably be mostly Python though, but I'm going to I'm trying to work on ML.NET more because I really like where this is going. And then there's my Twitter, and if you want to send me an email. Is there anybody who wants to pipe in with a question or leave one in the chat?
Hey, Doug. Hi, this is Joe. I have a question for you.
Sure.
So I know that I want to make a statement. I know the statement is wrong, but I want to hear your answer to it.
Okay.
With your expertise.
Okay.
So one of the impressions I've had about machine learning, as I try to characterize it in my brain, is I think to myself, okay, if I could write a program with thousands or tens of thousands or even hundreds of thousands of if statements, where if each if statement is one of the training conditions, then wouldn't I get a program that's roughly equivalent to what machine learning would do for me?
So what you basically described is an expert system. Because what you're talking about is you wrote a program, and all those if statements are, because remember what I said, if the temperature is 32 degrees or less, and if precipitation is equal to true, and if the month is January, and if the location is Chicago, then it's snowing. So basically basically in that situation, yes, what you have is a big if-else statement, the kind that they taught you, nested if-else statement, the type they taught you in CS 101 never to write, or at least conceptually. Yeah. So the reason why so in other words, yes, artificial intelligence, you've created a rudimentary artificial intelligence system. The reason it's not machine learning is because you explicitly described all of the rules for making the predictions. The thing that distinguishes machine learning is the automated training of the model, where the machine or the algorithm, it goes out and it decides what the rules are. It looks for all the commonalities and associations and relationships between the data, and it discovers the rules itself instead of having the programmer explicitly give it all the rules.
So are you saying that it determines its own rules, or are you saying that it just approximates the curve that fits all the test data?
So
because rules and curves are different, right?
Well, true. Okay, so when I say rules, I'm saying conceptually. Okay, I'm using that term conceptually. What happens is, so the theory, so kind of the theory behind machine learning is that anything can be represented mathematically by a function. And what's happening is when you're fitting that data when you're fitting that model to the data, you're actually you're trying to fit that model to the function that represents the training data. Okay.
Is it one function or multiple functions?
There are actually in Microsoft, I actually saw it just recently. There is actually a GitHub repo in which they are working on multi-model machine learning. So in which you're looking at, because some problems are so complex, they can't be described effectively by just a single model. So in a way, yes, you can have multiple models in an attempt to get better predictions. Yes, absolutely.
Okay, so to append my initial statement, if I had tens of thousands or hundreds of thousands of his statements, and if it didn't fit any one of those, then it would determine the closest approximation. Then that's machine learning.
No. Machine learning is when you automate the process of creating the model that's going to make the predictions. Whereas with artificial intelligence is when you create it all yourself.
Okay.
Yeah.
So
that's what distinguishes the two. Yes. Yeah. That's the distinction. And you used a word there also that I like to use sometimes: approximation. Again, like I said, when I ran that first example with the housing prices and ran it several times and got different answers each time, but they all kind of seem to gravitate around a single place. That's because that's the approximation part of it. Yeah. So what you're doing is you're trying to fit or approximate that function. Sometimes this is referred to as, well, especially with neural networks, it's referred to as function approximators.
Okay. Okay. And like I said at the beginning, I knew my statement was wrong, but I wanted to hear how you define the
Right.
difference. Right.
Right. Yeah. So the distinction between the two is, so the distinction, what distinguishes machine learning, it's that process of not having to be explicitly programmed.
Okay.
Okay. All right. Well, I don't want to keep everybody much. Again, thank you for Joe and Sam and Stephen and everybody. Thank you for having me. I hope that this was helpful, and please feel free to please feel free to follow up.
Yeah, I really like the way that you walked us through the code. I've seen too many ML demos where they didn't really show much of the code.
Well, okay. Well, thank you. I actually thought that was kind of a cursory overview of the code, because one of the things that I want to emphasize in this is that you don't always have to. Well, you don't always have to write the code to train the model, and that's what a lot of times people think. Oh my gosh, I've got to jump right into training a model. Not really, because you've got things like you've got the model builder. You can import a pre-trained model. You could bring a model in via Onyx. You saw how Loeb allows you to train a model. There are many ways to train models other than I will send the slides to Stephen, or actually I'll just put them up on my GitHub, and I'll send the link to Stephen for the slides. But it's not necessarily training the model, it's finding the right model. And especially today, you do not have to you don't have to write code to train a model. But because that model is, it doesn't matter how you get to the model as long as you get to it. All right. Well, thank you very much. And if nobody has any more questions, then we'll wrap it up.
Okay. Well, thank you. And I'll say, as we usually say at the end of all our meetings, drive safe.
Oh yeah, thank you.
Yeah, thank you, Douglas.
All right,
appreciate it.
All right, have a good evening, everybody.
Okay.
All right. If you haven't already, the link for the feedback survey is in the chat. I will also send that out via email later this evening. That survey will be open for 24 hours. So if you care to, please leave Douglas some feedback, and we'll get him the results of that.
I welcome the feedback, good, bad, or indifferent. And that is something that I do seriously look at. A lot of people sometimes think that presenters don't look at that feedback, and I make modifications to the presentations via the feedback. I try to do it as soon as possible. I'm actually doing this talk again next week, so I will definitely take feedback.
Excellent.
All right. Have a good evening, everybody.
All right. Thank you. Thank you very much.